So I've got to complete some thoughts here about the refinement equation, which dominated lecture 27, and bring in wavelets as the differences between the coarse scale and the fine scale. V0 is contained in V1, but there's some more stuff in there, and that's the details, because V1 has details in it that V0 doesn't have. And it'll be the wavelet space V0 that shows us those details. Then to discuss some applications, some of the many applications, and a very good question was asked before the lecture. How did Ingrid Daubechies, whose great paper was in 1988, what question was she asking herself, and what answers did she find? Okay. The question, she came out of physics and had friends in seismology. So, for example, a question that was in the air was, what kind of a basis could seismologists use to represent a fast pulse that stops? And Fourier basis was not any good for that. The signal was not suited to functions that go on forever. So it was natural to look for a basis. We want, among other things, we want compact support, finite length. Can I write it as compact support since I started to? Just because it seems reasonable that our basis functions, that there might be basis functions that are supported out here, and we want 0 of those. And then we kind of think of Haar as one answer. But so we wanted compact support like Haar. We wanted different scales, multi-scale like Haar. But then we also want somehow better than Haar, because Haar was 80 years old by that. I mean, not the person. The idea was she wanted to, better make it clear that it was Ingrid, improve on Haar. And at that point, it was natural to think about orthogonal bases as being quite good. So, and thinking of bases that were of that form. Some function to be found that whose dilates and shifts would give automatically multi-scale, would have compact support, and hopefully would be better than Haar. But it wasn't at all clear that such, and orthogonal. I'm going to add in orthogonal. So maybe we no longer are so insistent on that property. I remember writing a survey paper in Siam Review back at that time, of course after Ingrid's paper had appeared, and there was a whole lot of interest in it. And I remember asking Ingrid, well, do wavelets have to be orthogonal or not? And after some thought, she said, maybe not. And now we would say definitely not, because we know that in these applications we often want symmetry and we can't have orthogonality. But at that time she wanted orthogonality. So she wanted to create a basis that had these properties. And I'll write down in a minute what the Haar wavelet is. But it wasn't clear that you could, even how to tackle it. I mean, this is a bunch of functions, and how do you decide whether they're orthogonal and so on? I mean, it was like a real math problem where you don't know where you're going, frankly. You're waiting for some lightning to strike to give some idea. And now, of course, we do have a framework based on these filters in which it really, despite the confusion of all lectures in this series, is a much clearer picture, and there's a way to go. So that now, and Ingrid sort of began to find that way. Other people stepped in, MATLAB and others, Meyer. Those are some of the great names in this subject. In the seismic area, there was a physicist named Grossman. Yeah, all in France, actually, these guys. And then came Meyer, who's a great mathematician. His MATLAB, who's now senior, was a graduate student at that time, and of course Ingrid, and others. Yeah, the history is quite interesting. Oh, and you should know a book if you're interested in like reading the personal side of something like this. There's a book called, I think it's called The World According to Wavelets, by friend Barbara Burke-Hubbard. Maybe I'll put her name somewhere. So, okay, so world, I'll just say world according to wavelets. And she uses a hyphenated last name, Burke-Hubbard. And it's published by a local company, A.K. Peters. A.K. Peters. It's a Natick publisher and a very nice bunch of people. And this book has won prizes for sort of popular exposition. So it's quite fun to give you the story more than I could do in these short time. Okay. And now maybe I'll jump to what the wavelet is for HAR. Because we've seen the scaling function. It's the box function. The wavelet, well, actually, we could guess it if we knew this wavelet equation. You remember phi of t is the box? And now I'm going to take, I'm in the HAR context, so I just have two coefficients, plus and minus in the high pass filter, right? Plus and minus they are. So we take that combination of boxes and we get this. Again, it's from 0 to 1, and it's a box, half box, minus a half box. That's the HAR wavelet. So you see, wavelets have integral 0. So they're picking up oscillations where the scaling function is picking up averages. So this is maybe the key picture for this lecture, the key example. And in several ways. So let me jump into the wavelets here. Okay, and these spaces W, what I've called in the lecture outline, I've called WJ. So what is WJ? So WJ, fair enough, it's all combinations of the wavelets instead of the scaling function. Remember, VJ was all combinations of phi at scale j and the shifts. So it's a bunch of functions at that scale j. This is the same of W at that scale. So those are the W's, and these are the V's. Okay, now let me come to this with this example. let me put the box function in here too, just next to it. So this is the phi, and this is the w, both from 0 to 1. And here's the equation I'm shooting for, wanting to check that I take all the functions in v0 and all the functions and add to any function in w0, and what do I get? Well, the answer is going to be v1. These are the functions. These are piecewise constant on intervals. These are on unit intervals. So let's just draw one. So dot, 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 dot. For example, there I've got out 2. And what's in W0? Well, if I stay between 0 and 2, what's in W0 then? It's this guy plus any multiple. I'm taking any combination. Say this guy on this one. So there's a typical I'm just drawing one typical guy in V0 and a typical thing in W0. It's a combination of this and its shift with certain weights. Maybe that height's 2/3, maybe that height is 1.6, whatever. And I combine those. So let me put a plus sign in yellow here. For once, okay. And what do I have? What kind of a function have I got? I've got a function that's piecewise constant on half intervals, right? Clearly. Because this is piecewise constant on unit intervals, so automatically on half intervals. And this is certainly piecewise constant on half intervals, so I've got a result that's in V1. But now the point is, I can get everything in V1 from these two. Everything in V1 can be split. Here's the decomposition. Here's the wavelet decomposition. We know what a Fourier decomposition is. You split it into harmonics. The wavelet decomposition is you split the thing into multiple scales. So do you believe that I could take any function in V1? Why don't I have any function? Why don't I have all of V1 right here? Yeah, because the only functions I've got some functions in V1 here, but they're all plus minus, plus minus, plus minus. And here they're plus plus, equal. But if I mix the two, all I'm saying is that by combining 1, 1 with 1 minus 1 with the right weights, I can get any AB within, right? That's all I'm saying. Is that if I'm shooting to get something that goes up A and then goes up B, heights A and B, then some coefficient, multiplying this guy, plus some coefficient multiplying this one, would produce this one. And then on the next interval, new coefficient. Oh, no problem. So this is then, so let's go recursively. Because V1 plus W1 will be V2. What does that mean? This, my claim is that if I get it right at basic scale, I've automatically got it right at all higher scales. I mean, just these functions were functions of t or 2t. So just change t to 2 to the jt, and you've got it right at scale j. But now, look how we've got it. V0 plus W0, but wait a minute, is V1. But so suppose I plug that in then. Instead of V1, I'm breaking V1 down into V0 plus W0 plus W1 is V2. And now we're getting there. That's the multi-scale. Here's the averages. Here's the course details. And here's the fine details. And I guess that I'm realizing that a much more visual way to give this whole lecture would be to bring in the MATLAB toolbox, MATLAB Wavelet toolbox, and let you see these pieces. So that I don't know whether the lab has I know you have MATLAB, of course, but then there are all these. Sorry. Okay, and would I get that? Okay, and would that toolbox be in the thing? It probably is. Yeah. Well, so here I admit that I'm a mathematician and not. So I was talking hypothetically. Well, I could. I've seen it done so often, usually by my colleague, whoever that is, that I could probably do it. That really, I mean, so maybe let me check offline after this lecture what might be feasible. But what would we? Let's stay hypothetical in this for this additional minute. So what would that MATLAB toolbox? So it's the MATLAB Wavelet toolbox I'm speaking about. So that's one of its many toolboxes. One of the many toolboxes. By the way, so MATLAB, of course, is a product out of MathWorks in Natick. But they don't write the toolboxes. They hope that individual scientists around the world will think, hey, I know how to use MATLAB in wavelet theory. I'll write the toolbox, and then MathWorks pays the authors, which in this case were four additional French statisticians, not the ones I've mentioned. They created the toolbox, created the GUI, the nice user interface, and so that you could call up a signal. What's a signal? It's discrete actually, but it looks like a continuous function. And then you put the toolbox to work, and you say, okay, figure out its component at this level, its averages, and the piece. So you would, here's the we could say here's the function, and now the toolbox would break it into pieces. So it would have a piece that was very smooth. That would be the V0 piece, and then would have a piece that's, catching some of the oscillation. That would be the W0 piece. And then would have a piece that's smaller, probably much smaller in magnitude, but oscillating more rapidly, picking up the other oscillations. That would be the W1 part. And we could have like 5 scales, or we just tell the toolbox how many scales we want. 4 or 5 would be typical. And then you ask them to add these functions together, and of course they add back to the original. So what I'm saying is the toolbox, I'm writing things at the level of the whole space of functions, but what that means is for each function, just like for each function, just the way function has a Fourier series, it's got a wavelet series. And the toolbox would compute it. So what would the wavelet series be? It would use these functions, and it would use these, the V0, plus the W's at all scales. So the wavelet expansion of a function, just compare it with the Fourier expansion. That's the key idea here, is the difference between the Fourier expansion and this kind of a wavelet expansion. So we have some combination in V0 of its basis functions, and then we have combination of in W, but not only W0, but at also Wj at all the W's. So we need a double index Bjk. So it looks a little messier than the Fourier series, but it's the natural expansion in multi-scale. Okay.
How would you select the basis?
So we've selected a basis. Once we've decided on phi and W, we've got the basis. And where do phi and W come from? Well, now they come from H0 and H1. So your question, which is right on, is the thing is, the answer was in the previous lectures 25 and 26, I guess, which were about the construction of H0 and H1. And, oh, well, do you remember there that if we have an orthogonal basis like HAR, then there's another pair of filters that I called F0 and F1. And in the orthogonal case with HAR, they were the same numbers. But for other cases, they are different numbers. They come from these numbers by reversing signs and flipping the order, and it's all that neat trick. But did I answer the question properly? Let me repeat. Where do phi and W come from? Okay, that was Daubechies' question, of course. What the heck can I use for wavelets that improves on HAR, that's better than this square wave? And the natural idea would be that the wavelet should be longer, so that you see what will happen. The beauty of HAR was there was no overlap between W of t and W of t minus 1. They were obviously orthogonal because they didn't even overlap. But when the wavelet goes from 0 to 3, then the shift will go from 1 to 4, and they overlap in that middle region. And of course, the rescaled versions are all overlapping all over the place. So there's this incredible overlap, and you think, how could I ever do those integrals and make them come out 0? And I mean, it looks like just a can of worms. But the great thing is that if you construct your phi and W out of these, then these become the essential inputs that you have to decide on. There's your decision. What are the H0 and H1? And we compiled the equations that we wanted those to satisfy in order for things to come out right. And I don't know whether to recapture those equations. Again, I hate to add more equations here. But so I'll refer to the text and to the earlier lectures for the conditions. But the main point is, if we get an H0 and H1 that made us happy last week, then we've got a phi and a W that make us happy this week. That's it. Oh, well, we have a phi and a w in principle. Of course, when I say we have a phi and a w, it doesn't mean I actually know what phi is. I darn well know what h naught and h1 are. That's just a set of numbers. I don't actually know what phi and w are, and I don't want to know, frankly, because I don't need those functions. You may say, how could I do anything without knowing these functions? The point is, those functions came from these numbers. And if I can throw all questions and all calculations back to those numbers, I've got a good algorithm. Because there's just a finite number, small finite number, maybe 3, 4 of each, or maybe 9 of these and 7 of these or something. Seldom would I go much higher than that. Then I can work with those numbers and never need to know the function. But so that's really the whole idea is that everything now is seen in terms of those coefficients. And actually, let's see it. How would I? What is the relation between? How would I produce this function in V1 out of this function? Let me give you an example, and so where you have to tell me the numbers. Suppose my function in V1 is, let me give you a specific function, and you just tell me how many of each I need. Okay. So suppose I want to take a multiple. I'm just on one interval. Let me throw, because I do this an interval at a time. So let me just stay on the interval 0 to 1. 0 to 1, I've got the box function here, and I've got the square wave here. And I would like to produce, let's say I would like, so on 0 to 1, suppose I would like to produce 5, 3. On 0, 1. How much of the box and how much of the square wave should I put in to produce 5, 3? 4 of these. Let me do that even in yellow. 4 of these. And how much of the other? And 1 of those. Okay. Right. So you had no trouble to do that. But my point is, these numbers 4 and 1, you could have, what you could have done, should have done, is to take the 5, 3 sample, send it through, now you're going to remember from last time, send it through this low-pass filter, the H0 filter, and send this one through the H1 filter. And what would have come out? Do you remember what those filters? Well, this is a very short signal. I really have all zeros until it, and then all zeros after it to fit what I had before. So do you remember what? Yeah, this is a very good thing to do here. You remember what comes out? What's that filter again? The H0 for HAR? It's averaging, right? Half and half. Okay, so I send that signal through, and what signal do I get out of this averaging filter where it takes, so this filter takes half of the current plus half of the previous. Okay, so here come in a whole lot of zeros, and it'll keep averaging 0 with 0. And then the first time it sees this 5, it's averaging that with its guy before, so it gets what? 2.5. Well, who wants 2.5? Nobody, but it gets it. Then it averages the 3 with the 5, and it gets 4, the number we really want. Then it averages the 0 with the 3, and it gets a 1.5. So, and then it's zeros after that. So out comes a 5 halves, and then the 4 that we really like, and then the 3 halves that we really don't want, and all the others are zeros. Okay, but then do you remember what the filter bank did to that? It downsampled. It took every other one. So it takes this guy. It picks the right one out and throws away these, throws away a lot of zeros. And now down here, of course, this is the differencing filter. So it'll take 5 minus that over 2, 3 minus that over 2. Why am I getting, you see you see my trouble here. I'm getting a minus 1, right? I'm getting 3 minus 5 over 2. Why am I getting that? Because I've screwed up somewhere, right? Okay, yes. So, but it'll be the minus 1, which, so I've just, you know, you see how the patience required to, well, probably a minus 1 will come out of here. Yeah, I mean, so a minus 1 is coming out of there and a 4 is coming out of there. I could really fix that, or we all could fix this up. There's a flip in the between the analysis step, the H's, and the transpose, the synthesis. Anyway, the minus 1 would have to come out as the plus 1. But what was my point? My point is, yes, that we don't have to think about these functions. We can drop down to the filters. We take these values 5, 3, and send, or the sequence of values, send through the filter bank, and out come the numbers we want.
So that particular filter bank, those particular filters lead to the hard.
Exactly.
And if you took some other low-pass filter and matched high-pass filter,
right,
it would lead to
some other phi, some other basis, and the and
they're one-to-one.
well, that's what that last lecture was about. That if we had some low-pass and high-pass filter, it might, if it was a good one, it would lead to a basis. But that some of those numbers, as we said, sometimes don't. But not worrying about. I mean, let's take an optimistic view of life here. So yes, so if I take decent numbers, following, you know, then I can expect decent functions, and then everything will work. The expansion coefficients for the function are connected to the outputs from the filter, from the filter bank. Yeah, that's the beauty. That's what MATLAB observed. Really, I think so. It's sometimes called the MATLAB algorithm. Run it through the filter bank. So that's essentially what you do. So if we're talking about applications, what do? You get a signal. Suppose you want to compress it. Let me start with that application, compression. Okay. So what do? We get a sequence of samples of our signal. We send those samples through the filter bank, and we get wavelet. We get its wavelet transform at several levels. Of course, not infinitely many levels. Can't do that, but several levels. Then we compress. So then we're saying, okay, we won't keep the full series. We'll only keep terms that are worth keeping. And how to decide what's worth keeping there, that's where the signal processing engineer is, that's what he earns. That's where he earns his extravagant salary. Okay. And I mean, this is certainly an area, this telecommunications and so on, in which the demand for graduate students who know about this stuff is incredible. So so you've compressed, you've thrown away some of these coefficients and kept the ones you wanted. Then you go through the inverse transform, and you have or you you transmit or store or do whatever you want with the compressed wavelet coefficients, and then reconstruct at any time a function that looks pretty much like the original. It would be exactly the original if you kept all the coefficients, but probably you kept the largest ones, so it's not quite the original function, but it looks, the eye can't tell the difference. So that would be a typical compression, yeah.
For the reconstruction, you need those functions.
For the reconstruction, well, if I was going to get a real continuous time answer, I would. But in reality, I'm going to get a sequence of samples. When MATLAB's toolbox is drawing this picture, it looks like functions, but it's really it's working only with samples. Yeah. So that, yeah. So I suppose you could say that to draw this picture truthfully, you would need to know phi of t, because this is a combination of what I'm seeing here is a combination of the phis and their shifts. But all the calculations have to be done for a finite set of numbers, and those finite set of numbers, here we have half as many numbers, here we have, and so on. Yeah. Did we need another set of filters? We did. We did. That's right. That's right. Exactly right. In general, it's a second set of filters that I called F0 and F1 that did the reconstruction. So really the whole package is to know those. And as a matter of fact, now I'm telling you what I might have revealed at the very start. It's really the F's, because the reconstruction, as we're saying, is in terms of these phis, it's really the F's that enter in the scaling function and the wavelet that are really in this series. I am sorry to reveal that late, but you sort of saw it, why it's true. It's the H's that find the coefficients and the F's that put everything back together. So there's a scaling function, and so the full picture is that the H's, there's a scaling function that's usually written phi tilde that uses the H's, and a wavelet usually written W tilde that uses the H1s, but those are in the step of finding coefficients, so you don't really see them. Then in the reconstruction, it's the F's in discrete time and the phi and the W in continuous time. Right. So everybody's remembering. Maybe good if I rewrite the full filter bank. The signal goes through H0 and H1, downsampled. Then now we've done the transform. We compress at this stage. Now comes the inverse transform, upsample, and the other filters F0 and F1, and then put the pieces together, and you've got the reconstructed X hat, let's say. I'm just writing down what we were looking at last week. So the whole point is that these numbers that went into the filters are those very same numbers that go into the continuous time. These numbers gave a change of basis, you could say, gave the coefficients in a new basis. Then in continuous time, these are the spaces, and the phis and w's give the bases, but the coefficients that connect everything are still the same. Okay, let me give repeat the Daubechies magic numbers, because she was then the first to find numbers that worked. And may I just repeat what those numbers were? Her numbers were 1 plus root 3, 3 plus root 3, 3 minus root 3, and 1 minus root 3. Those were the H's and the F's. Maybe the F, the H naught and F naught. Maybe one is the flip of the other. I guess it is, right? Because, yeah, and that's where Haar got into a little trouble here with that flip. And then the H1 and the F1, so those, one is the, I use the same four numbers. Here, because Daubechies was shooting for orthogonal, she uses these same four numbers, but with sign reversals. By reversing every other sign, I do get a high-pass filter, and this guy is orthogonal to that guy, and the result of orthogonality of vectors is orthogonality of wavelets. So that was, but you might read that original paper by Daubechies. You might, if you, it's in 1988, Communications on Pure and Applied Math. So I'm Pure and Applied Math. It's the New York University Courant Institute Journal, and it's just a very striking paper for the amount of insight it brought and the progress it made on a problem that looked extremely tough. Let me go back to say again, that problem was to find a basis that was orthogonal and smoother than Haar and overlapping, so that these orthogonality wasn't at all easy to identify. And she found a way to deal with that problem, and now we've described what it led to in the following years. Okay, where are we? Do I want to say more about these applications? That's probably of the greatest interest. How would you enhance a signal, get noise out of it? Suppose you're using Fourier transforms. So we have a signal that's got noise, say Gaussian noise, white noise added in. How would we approach the problem of denoising that signal? Well, we would take Fourier transform, and we'd probably throw away high frequencies. We'd say those high frequencies, or in some way we would diminish them, because that's where the noise would be. Of course, we would be losing some signal. Yeah. That's right. So we wouldn't be, so the comment was, yeah, it would look great. We're smoothing it by throwing away those high frequencies. So it certainly looks smoother, but is that really the signal, the exact signal? No. No, because we threw away part of the signal when we threw away, and we kept some of the noise. Yeah, absolutely. So, and of course, we can't help it, because we don't know what that noise is. You know, so Wiener filtering gives the best answer if you assume time invariance, so that he can move into the frequency domain and the computation becomes very nice. We would say, oh, we'll move into the frequency domain, we'll just throw away the top or reduce the high frequencies. Well, how would you use wavelets? So that's the competition. How would I use wavelets to enhance a signal, get rid of the noise? Well, same thing. Take the wavelet transform, look at the coefficients. The V naught part I would absolutely keep. That's the smooth, averaged part. Most of the signal is in here. I probably would keep a lot of the W naught, but I'd begin to throw away some of the W1. You remember my picture of the MATLAB toolbox? I would keep the main signal, keep a couple of levels, and then start discarding, thresholding. Maybe I would just threshold. I would say, okay, any coefficient larger than such and such, I'll keep. Coefficient smaller, I'll throw away. Actually, orthogonality is a nice property to have if you're going to do it like that. Because you know, how does orthogonality pay off there? You know the energy, right? If you have orthogonality and you start throwing stuff away, you know you've reduced the energy. But if you don't have an orthogonal basis, then you're not so sure. If you throw away a little bit, it wasn't perpendicular to the rest, so the energy might have gone up, actually, by throwing that bit away. So, you can say, all right, do it anyway. Okay, it's because you're headed the right way. Yeah, by smoothing it out, right? And of course, everybody realizes that there's parameters to choose here to decide what's big and what's small, what's the threshold, how much will I keep of, how many bits do I want to keep? I mean, that's a big issue. If I'm doing actual, say, high-definition TV, well, I'm sending out signals in real time. I'm sending a certain number of BPS, bits per second. I can't keep more than that because I can't, I'll fall behind. So if you're compressing in real time, you know the bits per second, you know the compression rate that you're shooting for, and you have to reset the thresholds to hit it. So it's quite an exciting business. And so I would say probably with wavelets in the wavelet versus FFT competition, in video it's still mostly FFT because we know how to do that fast and we know what we're doing, and the hardware is all built and everything, and the chips are built. But in images, in still images, wavelets have moved in because, but still hardware to be built. I mean, a lot of, probably if these lectures are compressed before they go on the web, my guess is it would be the Fourier system that would compress them. Well, of course, it's video. But wavelets are moving forward. Why? Because wavelets give a better, if you do a lot of compression, wavelets hold up better. If you're only going to do a little compression, might as well do Fourier, I think. But for high compression, wavelets hold up better and Fourier falls apart. Okay. Are there questions or discussion? I mean, there would be applications that would interest you that I don't think to mention or don't know about. Yeah.
When we went through some filtering here,
Yes.
it really revolved around a projection onto a plane, out of a space onto a subspace.
Right. Can I repeat that for the microphone? That when we did in the previous lectures about filters, we were effectively, these steps were projection steps. And now, yeah, we're now projecting on, we're taking the V, the V naught component is the projection of the function into this space. And the W naught, the coarse wavelet component is somehow the projection into this space. But for me to say that and really mean it, I have to be in the orthogonal case. I mean, when I say projection, we're thinking perpendicular projection. That would mean that these spaces were orthogonal. It would mean that hey, our our V naught is some space of functions like this. Our W naught is some perpendicular space. You give me a signal. It's got a pretty big V naught component and a pretty small W naught component, but they're perpendicular. Okay, and this is for orthogonal spaces. And I get orthogonal spaces from orthogonal wavelets. I mean, the world of orthogonal is like self-contained and consistent. Now, biorthogonal, which is what I'm going to have to live with if I want symmetric filters, which I do want, then I've lost orthogonality. So now I'm into biorthogonal, and this W naught is sure enough independent, of course. But not now. If I take my signal, the projection is not 90 degrees, right? Between that space and that space, I get the whole thing. I've got non-perpendicular axes, and then I've got a signal that I want to. It's got a component along that and a component along that. But how do I find those components?
But that's the Whitening problem, essentially that.
That's right. That would be one way to say it. I'm in a. So one way to say it is these are perpendicular. If only I knew the right definition of the right norm, the right inner product, they would be perpendicular. But by the standard definition, they're not. Okay, in wavelet world, the answer is it's the F's that fix you up. You know, we've got sets. We've got H's and F's, and it's if we're not perpendicular, it's we need the other one. In other words, we have a matrix M, and its inverse, and its inverse fixes up M and brings us back to where we want to be. But in the orthogonal case, this would be just a transpose of this, very simple, and projections would be what we think of as projections. In the biorthogonal case, we need H's and F's to do it right. Yeah. So just to complete that picture, then, well, I don't know how to complete it. Somehow this vector has a component along here and a component along here, and that doesn't look too good, does it? How should I draw it? I guess I wanted to go a little further and then a little further backwards. You see, triangles aren't right triangles in biorthogonal case. Yeah.
What is biorthogonal?
It really means that I have two. Yeah, very good question. So that word biorthogonal means that I've got two sets of functions. Let me call them so I'll call them C's and R's. So some functions Ci of t, and some other functions Ri of t, and these guys are orthogonal to those guys, meaning that Ci is orthogonal to Rj if I is not j. So I've got two lists of functions, and you see that that's what we have here in a matrix, the rows of M and the columns of M inverse. So M has rows R1, R2, so on, and M inverse has columns C1, C2, and so on. And the fact that I get the identity says that R1 inner product with C1 is a 1, but R1 inner product with any of these guys is all these zeros. So it's like Mark Twain and saying we've been talking prose all our life and didn't know it. Similarly, we've been using biorthogonal functions all our lives, but without that word being used. Just whenever I have a bunch of rows biorthogonal to a bunch of columns, I've got a matrix and its inverse. Yeah. So it's, and of course, numerically, what we hope is that M isn't too far from orthogonal, that the R's are not too far from the C's, that the angle here isn't too small, that that we really have got a decent, well-conditioned splitting here, and or that these vectors don't, that this isn't nearly singular and this isn't enormous. We don't want, and with wavelets, we're okay. Yeah. So the biorthogonal symmetric wavelets like 9-7 are really not far from orthogonal, and the risks are not severe. Yeah.
I have an image that I want to compress.
Okay. Image to be compressed.
You seem to be saying that wavelets are better than for that.
I'm saying that if I want to compress it a lot, wavelets are better.
Is this an empirical observation or are there mathematical reasons?
Well, I suppose it's partly empirical because, first of all, you have to, the question is, what's an image? Right? I could only make such a statement with an idea in my head of what an image was, because if I allow myself, if an image is any set of pixels, well, there's no way I could choose one basis over another.
Is there some mathematical properties
Of wavelet.
think that they're probably going to be better for the type of problems?
That's the right way to ask the question then. Is there a way to identify the type of problems the type of images that we might have? And the answer is sort of yes, but everybody's still working on it. So statistical signal processing is studying the statistical properties of signals. And natural signals are very different from text signals, which are very different from computer-generated images. So they're all, so natural signals, and of course there's natural signals might be more or less textured. Texture means like your shirt would give much more, with all those checks, would be much more difficult to compress than my shirt. Right, that would be clear. So the more texture, the more high frequency, the more bits we need to reproduce it well. So coming back to the question, how would you describe an image or the type of a class of images that you might say, okay, take this class of images and compare mathematically Fourier versus wavelets. Okay, well, here would be one class of images. One way to tackle the description would be to say, okay, our image is a bunch of pixels, right? That's what it certainly is. And we could ask about the correlation between one pixel and its neighbor. Our idea is that those are probably pretty correlated, right? That if one pixel, there's some yellow on this shirt by now, but so it's not 100% correlated, but it's quite correlated. And of course, the higher that number, that correlation, the more regular the image that we're looking at. So that would be one way. Then we could say, okay, given a population of images where the correlation, so statistics is in here, where the covariance or the correlation between those two is high, then Fourier is going to do quite well. At least if you give it enough coefficients. But anyway, that's sort of the context in which a question could be asked. But And there is a quantity, so out of it came a rough number called the coding gain that a lot of signal processing engineers might use. It's a function then. It's got to be a function of the H's and F's. And it's not a bad function. So one rough way to decide is a base is good or not would be plug it into this coding gain formula and see if you get a bigger number than with some other choice. And that would have been built out of working with images with a certain assumed correlation there. There's a lot to do, and a lot I don't know about this area. But I hope that these lectures, first of all, give you some idea of what are the questions. And wavelets are part of the answer. But then images have edges. How do we segment them? This is a big problem. Give me an image. How do I identify the pieces that I should deal with separately? You know, shirt and tie. How do I find that edge? So do I do edge detection, or do I do region detection? Do I say, okay, start there and look around it for a region that's very like it, not too different, and it looks bigger and bigger. Then it touches the tie and it says, uh-oh, you know, I'm getting new. It's not well correlated anymore, so it draws the line that way. So that you can, so this segmentation, which is a key problem, can be based on looking directly for that edge or growing the region until it meets the boundary. And you can do that in the wavelet domain, so the wavelet coefficients wouldn't be very different as I move around my shirt, but then they would change when I hit the tie. I could do it with the Fourier coefficients. It's a wonderful world. And of course, I mean, one wish is that I knew a lot more of it. But maybe this is the right point to stop for today, having introduced that world. One more question, sure.
What's the relative computational burden of computing the
Wavelets,
transform?
of doing the transform versus Fourier, yeah. Well, of course, it depends on, I mean, if you've got a chip that's dedicated to Fourier and you haven't got a chip that's dedicated to wavelets, okay, it wasn't a fair, I think, given the same level of effort, they're quite comparable. Quite comparable. Of course, you're making a decision. If you use 9/7 wavelets, you're making a decision on how much computational effort's involved. But it just affects the constant. And if you're doing Fourier, you're deciding what size Fourier transform to do. That's a decision. I think a reasonable answer is that they're comparable. Yeah. Otherwise, the new IEEE standard wouldn't have. I mean, that of course is a highly important consideration. It has to be. The computations have to be efficient. Yeah. So that's behind all this. The fact that this wavelet, that this filter bank is efficient. Other question before we call it a day. Okay. So my final lectures are promised to be about optimization, including linear programming as one part, but only one part of a whole world of numerical optimization. How do you actually find the best, the smallest cost solution to some problem, the minimum of some function? So that will take us in a different direction entirely. And so that's it for today, except